Hi, in this video we are going to talk about this popular interview problem, trapping rainwater. We are given an array of non-negative integers, means the array contains 0 or positive values. The values represented in the array are heights of bars. So you have different bars of different heights. If your array size is 3, then there are 3 bars of different heights of given heights. The height of first bar is 2, the height of second bar is 0, the height of third bar is 2. So these are the bars you have. Now the question is how much water you can collect between these 2 bars. So there is a bar of height 2 and there is a bar of height 2 and there is a gap between these 2 bars and the height of this gap is 2 units. So that is how you can collect 2 units of water for this input. Let's see the next example. We have 5 bars. First bar is of height 3, then 0. So height 3, then 0 height, then 1 height, then 2 height and then 5 height. How much water you can collect? You can collect 3 units of water here, because if you put anything beyond 3 units, it will overflow, right? And you can collect 2 units of water here, and you can collect 1 unit of water here. So you can collect 3 plus 2 plus 1, which is total 6 units of water. Here are 2 more cases to explain the question better. If your array is in increasing order or decreasing order, you can collect 0 water. Because you cannot collect anything here because there is nothing to support this water on the left side. So water will flow down. Similarly here, you have nothing to support on the left side. So you can collect 0 water here, 0 water here. Similarly here in the decreasing array, you can collect 0 here, 0 here. So when your array is sorted in increasing order and decreasing order, the amount of water that you can collect is 0. Now please pause this video and try to think of a solution that tells you the amount of water that you can store for a given array. We are going to talk about different solutions. The first solution that we are going to talk about is big O of n square. Then we are going to talk about theta n solution. Let us first talk about naive solution to solve this problem. There are few interesting facts about this problem. One is, if you consider the corner bars, you can never store any water on top of corner bars. Because if you try to store anything on top of it, there is nothing on left of the leftmost bar to support that water. Similarly, there is nothing on the right of rightmost bar to support that water. So leftmost and rightmost bars, they can never store water. We can only store waters in the middle bars. Now we traverse through all the middle bars starting from I equal to 1 to n minus 2, because we know for I equal to 0 and I equal to n minus 1, we cannot store any water. Now, how much water we can store in the middle bars? How much water we can store here? How much water we can store here? And how much water we can store here? If you take a closer look at this problem, you will notice an interesting property. For example, if you see this bar, the amount of water you can store here is, what you do is you find the maximum value on left side, maximum highest support that you have on the left side, highest support that you have on the right side. So for this particular bar, we have maximum support on left side as 3, our L max is 3, and maximum support on right side is 5, R max is 5. Now how do we use these R max and L max to find the amount of water that we can store here? So how much water you can store here? You can store the water which is minimum of L max and R max, right? So minimum of L max and R max is it's 3. Now can you store 3 units of water? No. You can store only 2 units of water. So what adjustment we make into this result 3? We subtract the height of this bar, for which we are trying to find the water that we can store on top of it. So our result for this bar is, result for ith bar is minimum of L max Rmax minus array I. That's our result for ith bar. So for result for this bar is minimum of these two values, which is 3, minus height of this bar, which is 1. 3 minus 1, 2. 2 units of water we can store on top of that. Now what is the result for this? Let's do this again for this particular bar. The maximum height on left of it is again 3. The maximum height on right of it is 5. Minimum of these two values, Lmax and Rmax, is 3. And if I subtract the height of this bar from 3, I get 1 unit. So we can store 1 unit of water on top of it. Let's do for this. Lmax is 3, Rmax is 5. What is the minimum of these two? 3. And what is the height of this? 0. So 3 minus 0, 3 units of water we can store on top of it. Here is implementation of the same idea. We know corner 2 bars cannot store any water, so we begin from I equal to 1 to n minus 2. We find out the Lmax. What is the left maximum element for array I? So we initialize the Lmax as array I, and we find the maximum value every time for j equal to 0 to I minus 1. So for every element array I, we go through the left of it and find the maximum value. And we initialize the maximum as array I itself, just to reduce the number of lines of code. Then we similarly find right maximum. We traverse from I plus 1 to n minus 1 and find the maximum value on the right side. We initialize Rmax also array I. Now how much water we can store on top of the current bar? The amount of water that we can store is minimum of Lmax, Rmax minus array I. Now please note that Lmax and Rmax, if there is no greater element on right side of a bar, they are going to be same as the current bar. So you will get array I minus array I, and you will get 0 in those cases. For example, this input. For this input, if you consider this bar, left max is going to be same as height of this bar, which is 5. Right max is also going to be same as height of this bar because we initialize left max and right max as array I. So they both are going to be 5. And if we take the minimum of these two values, we are going to get 5. And we are going to subtract 5 from 5 when we are traversing this bar. So we are going to get the amount 0 for this bar. And that is what we want. So this program is a simple implementation to find the amount of water that we can store with the given bars. The time complexity of this program is theta n square. For every item, we are traversing on left of it, right of it. So we are doing n work for every index, and we traverse n minus 2 indexes. So it's theta n square. Now please pause this video and try to think of a solution that works in theta n time. Let us now talk about efficient solution. The idea of the solution is to pre-compute left max and right max. Rather than computing it for every index, we pre-compute it in theta n time so that whenever we need it, we have it available. And how do we pre-compute left max and right max? We initialize the left max 0 as array 0 because there is nothing on left of it. So that's the maximum on the left side. Now for remaining elements from 1 to n minus 1, we check if current element is greater than the previous left max. If it is greater, then we update the left max for the current index. So our left max of I is maximum of current element array I and left max I minus 1. And after doing this loop, we get these values in the left max array. This is 5. So current element 0 is not greater left max of I minus 1. So we take the maximum of these two, we get 5. Now we take the maximum of these two, L max I minus 1 and array I, we take 6. We take the maximum of these two, we take 6. Take the maximum of these two, we take 6. So that's how our left max array is built. Similarly, we build the right max array. To build the right max array, we traverse from the right side because we want the maximum element on right of every element. So we initialize right max last element as array element. So this 3 is same as this 3. Now we compare these two elements, and whichever is the maximum, that becomes the new right max for this element. For this element, we again compare this and this. So we compare array I and R max I plus 1, right? So we get the maximum of these two as 6. For this, we again compare the previous element and the current element of the array. Previous element of R max and current element of array. So 6 and 0, 6. Here, we again compare 5 with 6, right? Array I and R max of I plus 1. We take the maximum of these two, we get 6. So these are our L max and R max arrays. If you remember the naive solution, we needed L max and R max for every element, and we were computing it for every element. That is how it was theta n square. Here we are pre-computing them so that we get the time complexity theta n. So after pre-computing these, we use the same approach as we did in the naive solution. For every element, we find the minimum of left max and right max. Whatever is the minimum, we take that minimum and subtract the current element from it. So whatever value we get, we add it to the result. Let's do a dry run for this example. So we need to compute this result only for the middle bars. As we discussed before the naive solution, that we cannot store any water on top of corner bars because there is nothing on left of the leftmost bar to support more water. Similarly, there is nothing on the right of rightmost bar to support water. So we need to compute how much water we can accumulate for the middle 3 bars. So let's see how do we get the result 5 for this bar. So what we did, we took the minimum of left max and right max, which is 5, and we subtracted array I from it. So what is array I? It's 0. So we get this 5 as minimum of 5, 6, left max and right max minus 0. That's how we got this value 5. How do we get the value for this bar? We find left max and right max minimum for this bar also. So what is the left max for this? 6. Right max for this? 6. We take the minimum of these two values, which is 6, and we subtract array I. Array I is also 6. So we get 6 minus 6, 0 for this bar. That is how we got 0. How did we get 0? How did we get this value? Minimum of 6, 6 minus 6. So this is how we got this value 0. Now let's see this bar. What is the left max for this bar? It's 6. What is the right max? It's 3. So minimum of these two values, 6 and 3, minus array I. What is array I? It's 2. So minimum of these two is 3. 3 minus 2 is 1. That's how we got the value 1. So our result for this array is going to be 6. So that's how this naive approach works. The time complexity of this naive approach is theta n, because we are doing theta n work here, and then theta n again. And theta n plus theta n plus theta n is theta n time complexity. This solution requires theta n auxiliary space also. We have two arrays of size n, so we have theta n extra space in this solution.